Okay, part 2 of 4.2 is the word problems, basically. So this one's going to be pretty short. We're going to represent this word problem with the table, hopefully, words, an equation, and a graph. The table shows the relationship between the number of photos, X, that you take and the amount of memory, Y, in megabytes left on your camera's memory chip. Okay, remember that your number of the amount of memory left on your chip depends on the number of photos that you take. So this is your dependent, this is your independent. Is the relationship a linear function? And then describe the relationship using words, equations, and graphs. Okay, is it linear? Well, what we need to check is to see, is it changing by the same amount every time? That will make it a straight line, which is called linear. So how do I get from 512 to 509? I subtract 3. Okay, 509 to 506, also subtract 3. And 506 to 503 is also subtract 3. So this is telling me that every time I take a photo, because I got to check both sides. It looks like they're just taking one at a time. Okay, every time I take a photo, I subtract 3 megabytes of memory. So each photo is worth 3 megabytes of memory. Okay, so that might be what you want to write for your words, which they ask for in this slide. Okay, so for words, I'm going to put that each photo decreases my memory by 3 megabytes. Okay, those are your words. Equation, if I know that it's changing by -3 every time, okay, then we know that we for sure have a y equals a -3x, but we need to figure out what else we need. So if I take my first x and I plug it in, how am I going to get to 512? So if I put -3 times 0, what do I need to get to 512? Looks like I would have to add 512. And actually the best part about this is when you have a 0, that usually is what you have to add. Okay, so let's try it. If I plug in 1, -3 times 1 is -3. If I add 512 to -3, do I get the 509 that I want? Yes, I do. Okay, so my equation is going to be -3x plus 512. This graph would be a little bit crazy. We'd have to skip count by a lot. So we're going to go on the bottom 1, 2, 3. And I actually, if I were you, this little lightning bolt means that I'm skipping a whole bunch at the beginning of the graph. And I'm actually going to start my graph at 500. And then I can count by 2s, I think. 2, 4, 6. Yeah, 502. 504. All right, so 1, when I plugged in a 0, actually, because that was our first 0 pictures taken, I had 512 megabytes. 1 picture taken, I was down to 509. 2 pictures taken was at 506. And 3 pictures taken, I was down to 503. Linear function makes a straight line. All right, last example. Is the relationship in the table below a linear function? Now, they just turned your table to side, so don't worry. If you really have a hard time reading it that way, you can also change it to look like this. 0, 1, 2, 3, 8, 10, 12, 14. Okay, these are the same tables. All right, now I'm going to check to see if it's linear by making sure that it changes by the same amount every time. Looks like we're adding 2 each time, so I do know Oh, and these are adding 1. So I do know that it's linear. Okay, so yes, it is a linear function. Describe words, write an equation, and then graph it. If I describe this with words, for every input, when I go up by 1, my output is increasing by 2. Okay, so my words would say, for every input, every 1 input, my output increases by 2. Okay? If I were writing the equation, I know that I'm going to have y equals 2x. But what else do I need? So if I plug in a 0, 2 times 0 is 0. So I'm going to have to add 8. But I better make sure that that works. If I plug in a 1, 2 times 1 is 2, plus 8 gives me 10. 2 plus 2 is 4, plus 8 gives me 12. And 2 times 3 is 6, plus 8 gives me 14. So I know that this is my equation. And then my graph, I think you guys can handle the graph. Make sure that you have 3 on the bottom and up to 14 on the side. And we know that it's linear, so we know what it's going to look like. I'll let you guys graph that one on your own. Okay, does this set of ordered pairs represent a linear function? And explain. For me to see it, I like to put it into a table. Okay, so my first ordered pair, my x is 0, my y is 2. Second ordered pair, 1 and 4, 3 and 5, 1 and 8. Okay, one thing that we can check is to see if it's changing by the same amount. It has to be changing by the same amount on both the x's and the y's in order for that to be a linear function. So let's check. This was add 2. This was add 1. This was add 3. Not necessarily a problem, but we got to check out the x's. Okay, this is add 1, add 2, subtract 2. Okay, so what we want to look at is 2 things. First of all, if you notice, way back here in our definitions, it said that each input, or x, could only have one output, or y. So down here in this one that we're working on right now, this input belongs with a 4. But down here, that input repeats, and it's with an 8. So automatically, we know that this is not going to be a linear function. The other thing you want to look at when the numbers are skipping around like this, you want to look at both this and this together. Okay, you want it to be y over x. So our first change is a 2 over 1. Okay, y over x. The second change is 1 over 2. These are not the same thing. So we Does the table below represent a linear function? If so, represent it with a graph and an equation. Okay, first step is always just check to see if it's changing by the same amount every time. And remember that you need to do it on both sides in order to know for sure. Okay, over here it looks like we're adding 2 every time, which is perfect. On the x-axis, it looks like we're adding 7 every time. Okay, now because I'm not counting by ones, I can't just say that for every input, my output changes by 2, because that's not true. I need to actually look at the changes in y over x. So my y over x is 2 over 7 for this first one, and luckily happens to be the same for all of them. So I know that 2 over 7 is going to be my change that has to go with my variable. Okay, now I need to figure out 2 over 7 times 0 doesn't get me to 8, but luckily we get to start with a 0, so we know that we have to add 8 at the end. And if you try out the rest of them, I'll let you in on a secret that actually works. And this is our equation. Now to graph it, on my x-axis, I'm just going to count by 7s because that's going to make our life a little bit easier. But on the y-axis, I think I can count by 2s. All right, when I graph it, my first one is 0 over 0 up 8, over 7 up 10, over 14 up 12, over 21 up 14, and over 28 up 16. There's our linear function. Okay, very important that you're always looking at your change as a y over x. Back here, when we were only worried about the one side, that was because these were all changing by 1s. Oops, 1. So that meant our change was 4 over 1, which is just 4 anyway. So always check both sides so that you know what your actual change is to put into